What would happen if we gathered all the asteroids in the main belt between Mars and Jupiter into one planet? Today, in the Universe Sandbox simulator, we're going to conduct such an experiment. We'll merge all the asteroids into one object and see what size and mass the new planet will be. And after that, another interesting experiment awaits you. To merge all the asteroids, I'll have to use a little trick. First, I'll delete all objects in the solar system, including the Sun, leaving only the asteroid belt between Mars and Jupiter. Don't worry, after the experiment, I'll return the newly formed planet back to the normal solar system. The simulator is currently showing the orbits of the largest objects in the asteroid belt, but to display them all, I just need to select them like this, and now they're all visible. Next, I'll go into the properties of all these objects. Simultaneously, go to the motion tab and set the distance of these objects to 2000 kilometers. And now they've all gathered together like this, roughly speaking. I'll also reset the velocity for all these objects. This way, all the objects will fly toward the center and merge. I could also choose to disable fragment formation and temperature modeling in the various simulation settings, but for now, let's simply leave these parameters on. Starting the simulation, 10 minutes pass per second. Oh boy, look at those intense collisions, guys. So many fragments have been created. The fragments, as we can see, are just flying apart, and a lot of glowing hot gas has appeared. So, what do we have? Our series here has taken on an egg shape. Oh, it's so blinding. Wow. As you can see, the collisions created a lot of fragments and dust, so merging all the asteroids without losses won't work. I'll delete all these particles. If we look at its characteristics, the radius has only increased by 100 kilometers, and the day on Ceres is now just under 2 hours. This object could have become even larger if the fragments hadn't flown away and if Ceres hadn't melted like that. So I'll do it differently. In the simulation settings, I'll disable fragment and temperature modeling. I've also opened the properties for Ceres, since Ceres will be absorbing everything. Watch how the radius and mass of Ceres change here, starting the simulation. This time everything is colliding exactly as it should. There is no fragment formation or surface heating, so everything collides perfectly and very calmly. And you can see how Ceres just keeps getting bigger and bigger. Almost all the objects have fallen, but it seems a few have bounced off Ceres. And another interesting thing, these two objects just landed on the surface of Ceres and are staying there. Look, this is what it looks like. For the objects that didn't fall, I've reset their velocity, and now they'll definitely collide with Ceres. But look at the shape of Ceres, it's taking on an egg shape once again. And so, after all these collisions, Ceres looks like this. And in the end, we have a planet with a mass just over 4% of the Moon's mass and a radius of 573 kilometers. If we convert that to diameter, it comes out to 1146 kilometers. And a day on such a planet is just over an hour and a half, but I'll give Ceres a normal day. Let's make it 24 hours, just like our planet Earth. Essentially, this is the planet that resulted from merging all the asteroids of the main belt into one object. And now, as I promised you, I'll place this planet in our solar system in the normal solar system. To do this, I'll just save this planet. I've removed all the asteroids, leaving only Ceres. And now, instead of the usual Ceres, I'll put in that saved Ceres. Here it is, and I'm replacing the old Ceres with it. I've opened its specs so you can see it's definitely that Ceres with a radius of 573 kilometers. Now, let's compare this Ceres with other objects. First, let's compare this Ceres with the old Ceres. I'll place it right about here, and I'll use the chart mode tool here, and this way we can easily compare these two objects. On the right is the original Ceres, and on the left is the one that absorbed the entire asteroid belt. So it turns out this larger Ceres, which absorbed the whole asteroid belt, is only 181 kilometers larger in radius than the original Ceres. So the difference isn't really that big. Now I suggest we also compare it with Pluto. I'll place it randomly somewhere here. We can also compare it with the dwarf planet candidate Sedna. Let's also take the Moon for comparison. And we can also compare it with the smallest planet in the solar system, Mercury. I'll also use chart mode to compare the objects. And this is how it all looks. That's Mercury, the Moon, Pluto, the Ceres that absorbed the asteroid belt, Sedna, and the original Ceres. So what we get is that the newly formed planet, made of the entire asteroid belt, is slightly larger than Sedna, and the original Ceres, obviously. But if you compare it to Pluto, Pluto is much larger than Ceres, probably even twice as large. And if you look further, comparing it to the Moon, and especially Mercury, you can see for yourself what a huge difference there is. Essentially, this is the planet you get if you merge all the asteroids of the main belt into one object. As you can see, its size and mass turned out to be much smaller than one might expect. But that's not all. In the simulation settings, I'll enable fragment formation and temperature modeling. Since these objects are so close together, let's see what happens if we merge them too. And now, let's watch these collisions. Oh boy, that was epic, yeah. Mercury absorbed everything, of course. But the collisions are very spectacular and very hot. I'll speed up time at this point. Oh, what a bright cloud. This is how it all looks. We can already see liquid water on Mercury and clouds. Oh wait guys, I was wrong. I thought it was Mercury, but the simulator says it's the moon. So the moon won against everyone, I guess. Alright. The planet is cooling down rapidly now, and I see that even with such collisions the object didn't turn out to be that large. The radius is only 1,879 kilometers, and the mass is only 15% greater than the moon's. Apparently the collisions were so powerful that many fragments simply scattered. And the days are quite long on such a planet. 6.5 Earth days. Enough time has passed. The average temperature is minus 20 degrees Celsius and there are negative values everywhere. If we hide the atmosphere and clouds, we see essentially an icy world like this. There is a bit of liquid water and snowy continents. And on this side, everything is completely covered in ice. But there is one island that isn't covered in ice, yet there's no life on this planet. There's a lot of water vapor in the atmosphere, as much as 52 Earth atmospheres. There's a lot of nitrogen, more than 7 Earth atmospheres. The surface pressure on this planet is over 17 atmospheres, and the likelihood of life is just under 3%. There's no magnetic field on such a planet. I've got a great idea. Since we have an object like the moon here, let it be a satellite of Earth. And in Earth's orbit, let's see how this planet transforms. So, I've placed this moon around the Earth, started the simulation. The temperature began to rise. And here we see that the temperature is rising too much, and it's going to be very hot here. If I hide the atmosphere and clouds, these ices on the planet are actively melting, and the atmosphere will become even denser because of this. Earth's orbit is clear. Maybe in Mars's orbit it'll be something different. I'll put it, for example, right here. And it's better to create for these two objects. A barycenter. As we can see, the barycenter is right here, not inside Mars. And the moon is stably orbiting around Mars. Time is sped up to 1 month per second. And so essentially we can say the temperature here has stabilized and it's more acceptable. The average temperature is 54 degrees Celsius. It fluctuates a bit here, apparently due to the uneven orbit around the sun. But it's interesting to look at its surface, hiding the atmosphere and clouds. The liquid remains. The islands remain. But I don't see any vegetation or life anywhere. But it's still not bad, you must admit. There's quite a lot of water. And continents like these very distinct. But the planet still has a dense atmosphere. And after all, in Mars's orbit, the temperature here is the best. But the likelihood of life is still just under 3%. And here's Mars against the backdrop of this planet. So this is the kind of planet that eventually formed. If you liked the video, please give it a like and leave a comment. Thank you very much.